Excellent. Esteemed traffic flow expert, a student of Hani Mamasani. And Mike, you're going to want to unmute yourself. Oh, his microphone's not working yet? He can't unmute himself? Well, we'll try to read lips, Mike. But yeah, I remember listening to Mike when he was at TRB. I had a great presentation there before he graduated with his PhD. And now he teaches at UC Irvine, where Matt Dean also teaches.
Very good. Thank you very much, Cara, for the introduction to the moderator. Apologize for being late. My students or project scientists had a talk that I was answering questions in the chat from. So I'm very excited about this session. I reached out to the speakers beforehand. Some of them gave me bios, so for those that have bios, I'll read them. For those that don't, please give a brief introduction of yourself. This session is W13, Network Analysis and Infrastructure Systems. Our first talk will be from Chinonso Okorie, is a PhD candidate in industrial engineering at the FAMU-FSU College of Engineering, Florida A&M University, Tallahassee, Florida. His interests lie in the application of advanced OR, mathematical modeling, and data analysis to solving complex problems in transportation. I will hand it over to Chinonso.
Hi everybody, good afternoon. I don't have to introduce myself again because I've been introduced. So I'm going to be presenting one of my research work on network-based formulations and solution algorithm for paratransit districting. And so I'm going to walk through the introduction, literature review, briefly problem formulation, the approach we proposed, and some computational studies. So paratransit services are demand responsive kind of service offered to disabled
Chinonso?
customers. Yes, can you hear me?
I can hear you, but I don't see your slides. Do you have slides?
You said what? Sorry, I didn't get that.
I can hear you fine, but we can't see your slides.
Oh, you can, sorry.
And we'd also love
I
to
think,
see you on camera. So that's usually expected of presenters
okay.
if you have enough bandwidth wherever you are.
I actually thought I clicked on share, sorry. So yes, I'll be presenting my work on, okay, let me turn on my camera, give me a few minutes.
Take your time, and you're not in the full presentation mode in case you want to switch to that mode.
Okay, can you all see me?
Yes, yes.
Okay. So I'll be presenting one of my research work on networks-based formulations and solution algorithm for paratransit districting problem. And here is the walkthrough of my outline. So as an introduction, I would like to explain what paratransit service means. Paratransit services are demand responsive kind of service offered to disabled public transit riders who otherwise may not be able to use the fixed routes transit services because of their disabilities. And those kind of services are flexible because the route is flexible, unlike the buses, the regular buses that work on fixed routes and fixed schedules. So as of the year 1990, the US government enacted the law that these public transit agencies must provide those kind of specialized services for Americans with disabilities who cannot use those fixed route services. And now, for medium or small sized transit agencies, they can typically maintain a single paratransit service region, manage trip requests, coming from riders. But for large transit agencies, for example, we have the paratransit service region in Jacksonville, even in Brunswick area. But for large transit agencies, managing such amounts of requests is enormous. And to be able to efficiently deliver service and enhance service quality, those public transit agencies try to divide their service region into multiple zones, which each zone assigned exclusively to an independent contract or service provider to manage. For instance, you can look at the figure on your left, which is the paratransit service area in Massachusetts, Boston, which is divided into about 3 different regions, with the core being shared by the, the service providers. Now, if you also look at the figure in your right, that's another paratransit service area in Los Angeles, which is divided into about 6 different distinct service zones, with each zone assigned to a different operator. So the challenges with this kind of service is that the management zoning actually, when personal service is being zoned, it enhances service coverage, but it comes with a lot of inconveniences, like because when the rider is trying to move from one zone to the other, because different operators operate in these different zones, there is inconvenience of having to transfer between operators, moving from one vehicle, one operator to the other. And then at those transfer points, there's significant waiting time. So there's lack of coordination between different service providers operating at different zones, and then substantial waiting time at transfer points for those riders. So these are some of the challenges that come with zoning strategy. So I reviewed the literature and I found out that the practice of zoning, districting or zoning or design has been in effect and has been also studied in the literature. Even so, a practice like I showed the Boston area, the MBTA, transit agency providing different zones to serve customers, and also in Los Angeles as well. But the issue is that some of these zones are not optimized, right? So they're based off of their own idea of having to divide those zones and providing services, assigning those zones to different operators. But having to carefully design those zonal structures is something that has not actually been studied in the literature quantitatively, right? So a carefully designed zoning plan can actually enhance service efficiency and user experience, but there are no quantitative tools out there, quantitative or mathematical tools out there that can aid such zoning optimization or zoning design. Now, like I said in the literature, from the perspective of other transportation areas, this problem has been studied. But for paratransit, there is a practice of zoning, dividing service region into multiple zones, but there are no quantitative methods for doing this. And this is just a brief look at what we have, different type of zoning strategy existing for paratransit service. There is zoning with transfer and zoning without transfer. For zoning with transfer, we have a transfer point at zonal boundaries between operators, and then riders are transferred at those transfer points, to another vehicle serving their destination zone. For zoning without transfer, the operator has to cross the zonal boundary to drop off passengers at their destination zone. That is the current practice when it comes to transit services. But then when I reviewed the literature, I found out that even though the practice is existing, multi-zone structure is being adopted by very large transit systems, but there's limited literature on zoning strategy. Even those that have tried to study this practice, they use simulation analysis to solve the problem, but there have not been any mathematical optimization model that have been proposed to effectively define these zonal boundaries or design these zones in paratransit service. So based on that, I formulated two models, integer models. One is a base model and the other one is an extended model for dividing a service zone into multiple, dividing a service region into multiple zones, and also design an efficient solution approach that can help transit agencies to solve the problem for large-scale instances of trip requests. So for my problem formulation, I had just considered, for the base model, I considered an Euclidean space or 2D two-dimensional space where you could have this is service region and you have trip requests. And the trip request consists of the pickup point and the drop-off point, right? So you could see the different lines I have directed arrows, which are just trip requests, showing the different requests of riders. And then the goal is to find a partition or a boundary line that can divide the service region into two zones. I considered a case of two-zone structure, right? And then if any request crosses the boundary, then that is considered as a cross-zonal request or interzonal request. And every other request that are contained in either side of the service region is considered an intrazone request. So in a base case, we can try to divide the boundary in the service region in any kind of form, right? They can have boundary going in different ways, right? So we want to select the one that will help us minimize as much as possible number of trips crossing the zonal boundary. So, and I used some cross product rule to determine the relationship between a trip request and the zonal boundary, because I modeled a trip request as a vector, with a given direction. Also modeled the boundary as well as a vector, so going in another direction. Then I tried to look at the relationship between the two, that will help me classify whether a trip is crossing the boundary, whether it lies to the right of the boundary or lies to the left of the boundary. So that is a way for me to determine the relationship between a trip request and a boundary, and then properly classify them whether as a left zone request, right zone request, or crossing the boundary. So that is using the cross product rule. And then based on that, I can be able to populate my parameters because I had to define 3 different parameters. One of the parameters is where I decide, it's where I load trip requests that are crossing the boundary. It takes one, the parameter takes one if a trip request crosses the boundary, but it takes 0 if it does not. And then the other parameters that takes one if a trip request lies to the right, or 0 otherwise. And then the last one takes 1 if a trip request lies to the left of the boundary and 0 otherwise. So then I presented my mathematical formulation. Basically, I'm trying to minimize the total number of trips crossing the boundary because the goal is to select a boundary that will divide the service region into 2 zones and minimize as much as possible number of trips crossing boundary. And then we also want to ensure that workload is balanced between both zones, right? We do not have one zone assigned more trip requests than the other. So the deviation from the mean workload shouldn't be much. So I modeled that constraint using modeled workload balance constraint using constraint using constraint 5 and 6. Then, but for a realistic case, we also looked at the fact that a boundary is not a straight line. If you look at in reality, a boundary can be made up of different pieces, roadway pieces, which are connected, connected in segment by segment. It's not a complete straight line running from the northern border to the southern border. So if you look at this illustration here, you can see that the red arrow-headed lines are actually different roadway pieces that are connected, running from the northern boundary to the northern border to the southern border of the service region. And then we also have our trip request. So the goal here is now for us to select the roadway pieces that are going to form our complete boundary, running from the southern border to the northern border, also from the northern border to the southern border. And then, just like the base model, we're also trying to minimize as much as possible the number of trip requests crossing the zonal boundary as well. And then I also further, like I did in the base model, I also use cross products to determine the relationship between the piece request and between the request and a boundary piece, or which we call the roadway piece. But for this, it's a little bit complicated because we will have a relationship between a request and a boundary piece not intersecting. But then for us to actually determine whether there's an intersection, we have to solve a system of linear equations. So aside from a cross product to determine that a trip is intersecting with a request, but to confirm that, we have to solve a system of linear equations. So the relationship between the boundary piece and a request is more complicated than the base model. For to try to determine whether a request is intersecting, we have to solve a system of linear equations. Also determine whether the request lies to the right or to the left, then we need to look at the relevant boundary piece. So I did all those kind of analysis to properly classify whether a request lies to the right, to the left, or crossing a boundary piece. Then that way I can populate my parameters that I need for my extended model, right? Then I present here my extended model where, just like the base model, I'm trying to minimize as much as possible number of trip requests crossing the boundary. Remember here, our boundary is made up of different pieces of roadway pieces that are connected, to form a complete boundary. Now, it minimizing the total number of pieces crossing the boundary. So we're not talking about just a number of pieces crossing a single roadway piece. No, we're talking about the complete boundary. And then I also have some constraints here to ensure that there's a flow, like the boundaries are connected, using flow conservation constraints 11 here, and some other constraints that help determine what's the decision about whether a piece lies to the left of our complete boundary or lies to the right of our complete boundary. And then also have a constraint here, if you look at constraints 20 to 23, to actually determine what is the amount of workload, that is number of requests that are assigned to the left of the boundary and number of requests that are assigned to the right of the boundary, so that workload is balanced between the 2 zones. And then, because this model can only solve small instances of the problem, I found out that for us to solve large instances of the problem, we supply enormous amounts of trip requests. So we needed to develop a solutional approach that can help us handle the computational burden of solving large instances of our problem. So for this kind of, for the solution approach, we developed the heuristic, which can help us shift a candidate, generate new candidate boundary based on some existing boundaries. How does this work? So with the rate heuristic, whereby in the start of the problem, we generate an initial set of boundaries. Those boundaries are non-identical. So the boundary can be running in different directions. We generate so many of them. And then using a simple start approach, just solving different shortest path problem using different nodes from the northern border to the southern border. And then we'll now try to modify those boundaries to generate new boundaries. Why? By splitting each candidate boundary we generated in the first phase, splitting it into two, try to keep one part of the boundary fixed and then adjust the other. We might adjust it based on which zone has more workload than the other zone so that we can be able to balance out workload. So that is how we were able to generate more boundaries. So this kind of process is an iteration. It iterates multiple times. We keep trying to improve and generate new boundaries until we can be able to find a boundary that, you know, gives us a better workload balance. And so for the computational experiment, first of all, we try to generate a synthetic instance where we had a rectangular region. We try to first of all compare our proposed model when we solve it using a commercial solver with our proposed solution algorithm, right? So we generated a synthetic instance using a 20 by 15 rectangular region where we had 4 different layers. In our northern layer, we have nodes in a northern area, and then the second layer we had other nodes placed at level 10, level 5, and then level 0, which is our southern border of the region. And then we had 4 different trip generation and trip production zone or area in our service region. So we have areas where we have high density of trips originating and areas where we have high density of trip production. So that way, this is like a distribution of our origin destination flow. So we're trying to look at how we can generate trips, where we have high trip production and high trip attraction. That way, when we try to solve our problem, we try to observe whether our boundaries we're able to split the service region into 2 and then properly balance the workload. So we solved using a solver for a benchmark instance. And then we discovered that, for instance, that we had a parameter that we defined, which is epsilon. We used to control the amount of workload assigned to a given zone. So we are saying that this parameter is a threshold, relative threshold percentage that we used to control how much percentage the deviation for the mean workload can we allow for a given zone. So when we vary the parameter, we changed it slightly. When we varied it, we kept the parameter to like 0.4. And then we look at how the boundary looks like. We can see that we have more workload, which is more trips assigned to the right, to the left of the border of the boundary. Sorry, the left of the boundary, the left zone, and then we have less workload assigned to the right. And then when we also change the parameter to 0.2, we also observed that the workload is more balanced when we have stricter requirements for that parameter. And then we also compared the solution by our solver with our proposed solution approach. So we found out that for smaller instances, the solver can be able to solve the problem within our time limit. And we compared the solution with that of the proposed solution algorithm. We found out that the gap, it's minimal, under 2% for most of the instances. But then when we now get to very large instances, we see that our solver is not able to solve the problem within the time limit. And then that is where our solution algorithm comes in, and we're able to solve large scale problem where we supply thousands of trip requests. So then based on the fact that our solution approach performed well, we want to compare the computation time as well. So we try to use the solution approach for a real-world case study. Then for our real-world case study, we considered an anonymized network of a metropolitan area here in the northern part of the US. So a network of about 175 candidate boundary pieces. So here, if you look at this network, we have some purple nodes here, which are actually border nodes in the northern part of the region. And then we'll have this orange node here, which are border nodes in the southern part of the region. So the network arcs you see in here are boundary pieces. It forms a network. These are roadway pieces. So any of these roadway pieces can be selected as part of the boundary to run from the north to the south so that we can properly divide the service region into 2 zones. right? So we now try to visualize the distribution of our trip requests. So we have the pickup locations of our riders and our drop-off locations of our riders. If you look at it, we see that somewhere around the southeast side of the region, we have more trips, trip origins and trip destinations. So we used about 4,200 trip requests for our case study. And then we first had to select a subset of trips because we found out that for us to also compare to know whether the solution algorithm can also give us a good result that it gave us for the synthetic instance. We also have to select a subset of travel requests, of 4,300 travel requests, which are about 2,000 travel requests, and first solve using the solver and then solve using the heuristic and compare both to see whether we can also get quality solution, just like we did in the synthetic instance. So for the 2,000 sample trip request, we can find out that the solver actually the heuristic matches the solver result closely, about the maximum of 2.9% difference when you look at the optimality, 2.9% difference across workload balance. That is, we try to vary our workload relative threshold parameter that controls how much workload we assign to each given zone. And then we found out that for most cases, the maximum difference we can observe is about 2.9%. Now, our solver takes about 1 to 6 hours for this case to solve for each of the instances that we saw, but our heuristics finds these results within 3 to 4 minutes. And then we now use this heuristic, for the 4,300 trip travel requests we have in our region. Then we found out if you look at this map, you can see here that most of the trip requests where you have high density, where the color density is there is very high. That is where we have very high amounts of trip origins and destinations. So the higher the density of the color, the more trip requests exist in that given area. So then we also try to look at the number of trips as well, originating and ending there. So that's why we have 970 here, which is the highest at the core of the service region. So this is using the whole full trip request, about 4,300 trip requests. And then we also try to now use the heuristic now, since it performed well on an intermediate case, we try to use this heuristic to solve this problem while varying our relative threshold value. So we varied it between 0.2 to 0.4. So we see here that when we keep the relative threshold.
Chinonso, 1 minute left, okay? One minute. You're on mute now.
So we found out that the boundary shape changes, and then when we change it to 0.4, the boundary shape as well. Okay, we'll find out that more trips are assigned when it's 0.2. More trips are assigned to the right zone than to the left zone. When we change it to be 0.4, we also found that the boundary shape changes. Essentially, we are seeing here that depending on how much workload balance you want to, how perfect you want the workload balance to be, you need to control the value of the threshold parameter, which at smaller value, you have more balanced workload. At higher value, you have more flexibility of assigning more workload to a given zone compared to the other. So in conclusion, our study is the first to propose a quantitative approach to paratransit districting. And then we also were able to propose a heuristic approach for solving the problem where it's impractical for an exact solver. And further, our solution approach, we experimented it on a real-world case study using over 4,200 trips that it can give a solution under 7 minutes compared to a solver. Thank you. That's all from me.
Thank you very much. You have a question in the chat. I have one that I'll add as well, but we're going to move to the next presenter, please. Our next presenter is Mohammad Adnan Rahman from the Bangladesh University of Engineering and Technology. I'll let you introduce yourself a little bit more before you give your presentation, Adnan.
Am I audible?
Yes.
Can you share my screen?
Looking good. Yes, good.
Okay. Thank you. Hello, everyone. I am Mohammad Adnan Rahman, an undergraduate student from Bangladesh University of Engineering and Technology, BUET. I'm also an undergraduate researcher from TRIPS Lab in BUET. At the same time, I'm the General Secretary of ASC Student Chapter, BUET. The title of my presentation is Decoupling Road Network Structure and Transport Emission Patterns, Entropy Insights from a High-Resolution Inventory in a Data-Scarce Megacity. Before starting my presentation, I want to say thank you to the BUET organizing committee, because through this initiative, undergraduate researchers from third world country like me have got this nice opportunity to present our research to the whole world. So here is the list of my authors. All of us are undergraduate students. 3 of us are from BUET and 1 from Jahan University. So first, I want to walk you through the underlying story behind my research. And here I want to say that once I have heard that Dhaka city, the city where I live in, is one of the most unlivable cities in the world. And that situation has not been changed yet. As we can see in the IQ air ranking, Bangladesh has one of the worst air quality. That makes me thinking, what is the culprit behind this worst air quality? What I have found is really interesting. A significant portion of this emission is actually coming from road traffic, the transport emission. That takes me into another question. What are the factors behind this extremely high transport emission in Dhaka city? While analyzing the transport emission data of Dhaka city, I have found that actually there is no data. So that is the problem in case of data-scarce megacities of Global South, that we do not have any regularly updated emission inventory framework. But the fact is, Dhaka is not the only data-scarce megacity in the whole world. In case of India in 2013, they have developed the VAPI framework, which is the Vehicular Air Pollution Inventory Framework. This is not that much data intensive. Rather, it mostly depends on open source data. So there is a nice scope to use this data for Dhaka too. But there is one problem. That is, this framework is based on Indian emission factors that cannot be readily used for Dhaka, because Dhaka has its own traffic signature. Our roads are basically afflicted with heterogeneous traffic system. There is no lane concept. We have motorized and non-motorized vehicle running on the same road. So our traffic actually very unique, and it's different from other parts of the world. Luckily, this problem has been solved by one of my own teacher, Shada Khan sir. They have developed representative driving cycle based emission factors for Dhaka city. These are the local emission factors for Dhaka city, which accounts for the unique traffic signature for our roads, Dhaka roads. As Shada Khan sir is actually joining Karakokalman's laboratory. I think she is here, and I wish all the best for Shada Khan sir. Okay, so I have already stated about my study area and why Dhaka is the best case to study transport emission patterns. So that takes me to the first part of my methodology. I have combined the VAPI emission framework with the probabilistic representative driving cycle based emission factors developed by Shada Khan sir, and ultimately I have got the city scale transport emission. But the problem has not been solved. We have only got the data. Our objective is to connect this transport emission with the policy framework. In order to do so, we need the spatial distribution of transport emission. And for this problem is also actually be solved in the literature. We have so much variables that we can use to spatially downscale the transport emission. And definitely all these variables are not available for Dhaka in open source. So I have actually selected 3 variables that are population density, land use, and road density, which are available open source for Dhaka. And using this, I have developed the spatial distribution of transport emission patterns. And this is the second part of my methodology in a grid of 1 kilometers. Now, if we get the spatial distribution, the problem is not solved yet. Here is an example of this spatial distribution. As we can see, by just seeing this, we can say that where the hotspot is occurred. We can say that the location of the hotspot in this place, but we do not know how much clustered it is. We cannot quantify how much hotspot dominated or how much diffuse is the spatial pattern is. That's the actual case when the entropy comes in. You can also say that we can do hotspot analysis using GETIS or GI-star or Moran I, but the problem is GI-star answers where the hotspot sits, the location, not how much concentrated the whole distribution is. At the same time, Moran I just answers it is a spatial autocorrelation tool, so it answers whether the value clusters or not. It is a global number, not a measure of dispersion. But on the other hand side, if we use Shannon entropy, we can get a scale of 0 to 1. And we can say that if the value is near to 0, the pattern is hotspot dominated. If it is near to 1, we can say that it is near to diffuse. Also, we can quantitatively determine how much hotspot dominated or how much diffuse is the pattern actually. So as we have introduced the idea of Shannon entropy here, from this slide, our research turns into an interesting direction. Almost every transport emission studies are actually modeled based on the demand side. They have actually modeled based on the activity, the data got from the OD survey, and so on. But in my research, we want to see transport emission from the view of the supply side, the road network. So the objective of my research is that what is the relation between road network and emission pattern? Not the magnitude of emission. The magnitude of emission is already done by different literature. As we can see here, Boeing is a great name here. But my contribution is to relate the road network with the emission pattern, not the emission magnitude. So there comes the final part of my methodology, where I have selected 3 variables: intersection density, average node degree, and straightness, to characterize the road network structure and relate it with the normalized Shannon entropy, as I have discussed earlier. Basically, these 3 variables are also used by Boeing, about which we were talking about the previous slide. And that's the final part of my methodology. So for the network analysis part, I have collected the polyline data of Dhaka's road transport from the OpenStreetMap. Then I have generated the nodes of this polyline. And finally, I have filtered the actual intersections between these nodes. And thus, I have got the node-to-edge representation of the Dhaka's transport network. And using this figure, I have calculated those 3 variables that I have said earlier. So here is the list of my datasets. All of these datasets are actually open source. So these are highly reproducible for any cities that lack data. And this is the descriptive statistics of my datasets, because our reviewer said that I need to put a descriptive statistics. So here is the descriptive statistics. One thing I have to notice here is that we have 1294 cells for population density, road density, and built-up share. But when we have turned into the network analysis, we have reduced the number of grids, because if we use that much grid, there is no meaningful network representations. So we have changed the grid number for the network analysis part. Now, here is the result. As we can see, the truck vehicle has the highest number of emission share in case of Dhaka. So actually, truck is the culprit that I was finding since the first slide of me. And you can also see that the nitrogen monoxide and carbon monoxide emission has been raised to a great number, which is actually well above the IPCC guideline. So this is really an alarming factor for Dhaka. This is the spatial distribution of our transport emission inventory. And actually, this is the first ever spatially distributed transport emission inventory for Dhaka, which is solely based on open source datasets, no field survey. So actually, I think that is our one of the most important contribution. And the framework is also generalizable for other data-scarce cities of Global South. Okay, as we have discussed earlier, the spatial distribution cannot be directly linked with the policy implication. For that, we need the entropy definition. As we have calculated the Shannon entropy of Dhaka's transport emission, we have found that actually the transport emission is the emission entropy is very near to 1. That means the pattern of transport emission entropy of Dhaka is actually diffused. It is not at all a hotspot dominated. Why this is so important for policy? Because if we could find that the pattern is actually hotspot dominated, we need to more focus on localized policy interventions like low emission zones, congestion pricing, which have localized effect, specially targeted. But we have found that the emission pattern is actually citywide. It is diffused. So we should rather focus on city-wide policy measures, emission mitigation strategies, like vehicle electrification, increasing the level of service of transit, etc. And that is our headline result, the model performance of OLS regression. We have found that the R-square value is very close to 0. That means there is no statistically significant correlation between the emission entropy and road network. So from this point, we have said that there is a structural decoupling between the emission entropy and road network. And finally, there is the validation. For validation, we have used remote sensing data, the tropomy column N2, and we have used percentile correlation method, which is introduced by Goldberg. And we have also obtained an R-square of 0.8, which is also consistent with the previous literature of Goldberg, Laurent, and Wu. So finally, we have got policy implications that the transport emission pattern of Dhaka is actually diffused. So localized policy measures cannot fix Dhaka's air quality. Rather, we should introduce city-wide policy measures like vehicle electrification, increasing the fuel efficiency, and increasing the level of service of transit. Also, electrification must be paired with renewable energy generation, otherwise the benefits will be eaten up by coal emission. Finally, from the structural decoupling, we can say that this heterogeneity pattern is not locked into the road network. Rather, then this might be dominated by the travel behavior or the demand side variables. So that's the end of my presentation. Thank you so much for your attention. And if you have any questions or collaboration idea, you're most welcome.
Thank you very much. I think very interesting research question you're tackling here. Let's see if we have anyone that has questions. Okay, I'm going to take the time to ask a question then. So it seems you built this regression model, but it seems to me, given that you already knew that your Shannon entropy value was close to 1 for the region, that we kind of knew there wasn't going to be any structural relationship between spatial emissions and the network structure. Or is my thinking correct here, or am I missing and overlooking something?
There is actually a difference between the total emission entropy and the spatial distribution of emission entropy, because this one value is actually the addition of different grids, the 29 grids I was talking about. And so there's a difference, like 1 is the total value. So yeah, that means we do not correlate the value 1 with the my transport network structure. Rather, we correlate the pattern that we have got in different grids with the similar values we have got for transport network in those grids.
Okay. I think I got it. That's not your problem.
Thank
That's mine. Other questions from the audience? Okay, if you have them, if you're writing them up, Adnan, you can look for them in the chat, and we will move to our third presenter here, Tahseen Bashir, PhD student in Civil Systems Engineering at the University of Naples, Federico 2. His research focuses on road network vulnerability, resilience, game theoretic transport modeling, and high-speed rail systems. He received the Best Research Gold Award at the International Symposium on Sustainable Urban Transport Systems in 2024. Please go ahead, Tahseen. We can see your slides. I can't hear you if you're trying to talk.
Now, can you hear me?
Can hear you now, yes.
Okay.
If you could turn your video on, that'd be great. If not, I understand as well.
Okay, I will. Let me turn on my video as well.
Thank you.
Now it's okay. Let me share. Okay.
Good, we can see it full screen.
Okay.
Good.
Okay, thank you so much. Thank you, Professor Highland, for my introduction, and good afternoon, everyone, and good evening from Italy. And today I will present our work on Naples Metropolitan Road Network of Italy. And the main idea of this work is to identify road network segments that are important not only because of their position in the road network, but also because of how actually traffic uses them. So for this idea, we combine flow-weighted centrality measures with traffic flow obtained from static user equilibrium assignment. So our main focus is on vulnerability under disruption, particularly how critical nodes and links can affect travel time performance. So before going deeper into the discussion, I would simply start with this basic question that what makes a road segment critical? So a road segment can be critical because many shortest path passes through it. It can also be functionally critical because large volume traffic depend on it. And lastly, it can also be disruption sensitive if its degradation increase travel time, cost, or worsen system network performance. So the question is, which of these is sufficient on its own for the planning decisions? So the answer to this simple question is none of them is alone. In this study, criticality is strongest when network structure, traffic flows, and disruption impacts align. So this is why my today's discussion moves from network structure to traffic flows and then to disruption impacts. This is the core logic of our work. First, I will explain that why a pure topological view is incomplete for road network vulnerability. Then I will show how flows from static user equilibriums are embedded in the directed weighted graph. And finally, after, I will explain how centrality measures are used to rank candidate critical nodes and link. So I will start with the motivation that why topology is alone not enough. A road network is not only a physical graph made up of only links and nodes, it is also a use system which is shaped by a traffic demand and route and path choices. Topological metrics can tell us that which elements are well connected or lie on many shortest paths, but they may miss how traffic is actually distributed in the network. This matters because a node may look central in the graph while carrying limited traffic. Another node may look less central but carry high demand. For this reason, this work combines network structure with equilibrium traffic flows. The next slide will translate this motivation into the research objective and its contribution. So the main research question is, which network segments are both structurally central and functionally important under equilibrium traffic conditions? The objective is to obtain nodes and links whose degradation can reduce accessibility, redistribute flows insufficiently, and increase congestion. The contribution of this study is not that we invent a completely new centrality measures, rather we apply the established traffic assignment and centrality methods together in one flow-informed framework. Now I will briefly introduce the case study, which is the Metropolitan Road Network of Naples, situated in Campania region, which is characterized by urban dense road network. It covers approximately 1,179 square kilometers of area and includes more than 3 million inhabitants across 82 municipalities. For transportation modeling, we divided the whole metropolitan area into 112 traffic analysis zones based on the population and land use distribution. The network includes urban roads, regional motorways, the Autostrada del Sole and Tangenziale di Napoli, which is the motorway of this network, which makes Naples a useful case because it combines dense urban road network with major motorways corridor. Next, I will show you the spatial structure of the network and the traffic analysis zone. As you can see clearly, this map shows the spatial framework used in this analysis. The traffic zones define the origin and destination structure of the demand model, while the road network includes different road types from urban road to motorway links. This is important point we're here because that in the analysis, this analysis is not limited to just isolated links. It looks at how traffic moves across the metropolitan road network. Later, you will see in the result that one corridor becomes particularly important, and which is the A3 Napoli-Salerno corridor, which connects the urban core with the southern eastern metropolitan area of this city. To analyze this network, the next step is to represent this spatial this spatial connectivity as a directed weighted graph. So we converted the road network into a graph representation, and you can see that node represent the intersection, while the link represent the directed road segment. Direction here matter because traffic condition can differ by direction, and the key point is how the graph is weighted. Instead of using only the physical distance or simply connectivity between nodes, each link receives a weighted based on equilibrium traffic flows from the assignment model. So this graph represents both the structure of the road network and how the network is used. Static user equilibrium traffic assignment. Here I will explain like from where these equilibrium flows come from. So the traffic flows come from, we generated the traffic flows in a microscopic traffic simulation software, which is the PTV Vision, using static user equilibrium assignment. The basic idea here is the traveler chooses route that minimize their own travel time based on the wardrobe first principle. At equilibrium, users do not have the incentive to switch path alternatively because changing path would not reduce their travel time cost. For this work, the important output is the equilibrium flows on each link of the network. These flows become the weights used in the centrality analysis, which I will explain in the coming moments. So after weighting the network with equilibrium flows, we use several centrality measures to identify the critical segment within this network. And you can see there are 4 combinations of centrality measures such as betweenness, closeness, eigenvector, and Bonach centrality. And we use these multiple measures because it is important that no single centrality indicator fully capture road network criticality. The next step, we have to test whether the identified element actually matter when they are disrupted. Disruption simulation procedure. As you can see that centrality gives us critical segment, but it does not by itself prove that they cause performance loss. So the procedure is simple to select high centrality node or link, apply a disruption through a removal or capacity reduction, then recompute the user equilibrium assignment and compare the disruptive state with the baseline state. This step is important because it connects network ranking with actual performance degradation. So to measure this degradation, this study uses travel time-based performance indicator. Performance degradation matrix. So system performance, we evaluated using the travel time indicator. And the main idea is that if a disruption increases the total system travel time or link travel time, then the network is experiencing efficiency loss and congestion amplification. This metric helps us to move from this segment look central to this segment produce measurable travel time impact when it is degraded. Before showing the result, I want to frame the main interactive question here, like from ranking to planning, node or corridor. So after ranking high centrality element, the key question is that how we can interrupt them. Are we observing isolated weak points in the network, or these elements is a part of the connected vulnerable corridor? And this distinction matters for the planning purposes. Like if the risk is isolated, so intervention can focus on those specific points. If the risk is corridor-based, so planning should focus on corridor-level reinforcement and redundancy. Critical node cluster along the A3 Napoli-Salerno corridor, and the map results suggest that the second interpretation is more appropriate, which is the corridor level disruption. And you can see that the top 200 nodes ranked by flow weighted betweenness are not randomly distributed across the network. Here I just reported one centrality measure, which is the Bitfunis, and they show a clear spatial concentration along the southern metropolitan corridor, in particularly the A3 Napoli-Salerno motorway and its connecting arterial structure emerge as a primary backbone of this road network. This result is important because it suggests that vulnerability is not simply attached to isolated nodes. Instead, several adjacent elements form a corridor-level pattern. The ranking of the highest centrality nodes confirm that this is the corridor-based interpretation. Now you can see this table shows the 5 highest ranked nodes by flow-weighted Bitfunis, and the important observation is that all 5 nodes are located on that same motorway, and their Bitfunis values are quite close to each other, which range from about 0.035 to 0.039. And this narrow range suggests us that the corridor functions as a connected sequence of the critical element rather than one isolated weak point. Now here, the next question is whether this structural pattern also produces measurable travel time effect under the capacity reduction of each links. Let's see together. Now, this is one of the main numerical findings of our analysis. And when we reduce the capacity on different nodes, which is the top 5 highest Bitfunis nodes, so the travel time on the main segment increases by 6.8% for that specific link, which is from 37,900 to 37,894 node. And you can clearly see that the upstream A3 link also show a notable increase of 2.39%. However, the adjacent RAM link show almost no change, around 0.01%. So this means that disruption impact is not evenly spread across nearby link. The main motorway segments are much more sensitive than the ramps. And this effect also weakens when we go towards downstream, which confirms that vulnerability is partially uneven. And these results show that the strongest vulnerability appears where structural centrality and traffic flows combine together. So now vulnerability is concentrated where flow and structure align. So the A3 corridor shows us that this is critical because it combines high structural centrality with the concentrated equilibrium demand. The next one is that the critical nodes matter mainly through the motorway links they connected, and that is why the resilience loss is not uniform across the whole metropolitan network. It is localized along high flow motorway segment, which is the A3 Napoli-Salerno motorway. So our analysis shifts the attention from a single node to a corridor level interdependencies, which has direct implication for how the framework can support the planning decisions. Now, how this framework support the planning decision? So the practical value of this framework is that it can support early screening of vulnerable element from infrastructure prioritization, monitoring and maintenance, redundancy analysis, and the transferability. So for the Naples, the A3 Napoli-Salerno corridor deserves particular attention as a structural and functional backbone. Limitation and further research. So the current analysis which we did focuses on vulnerability and performance degradation after disruption when we reduce the capacity of each link. It does not yet model recovery or adaptation over the time, which would be necessary for full resilience assessment of the whole network. Also, the static user equilibrium provides a consistent baseline, but it does not capture time-dependent congestion propagation. Future work should therefore include dynamic flow redistribution, sensitivity analysis, uncertainty testing, and comparison with simpler benchmarks such as pure topological or flow-only rankings. To conclude, this study integrates static user equilibrium traffic assignment with flow centrality measures. And in our case, the Naples applications show a clear concentration of critical nodes along the A3 Napoli-Salerno corridor, and the capacity reduction results show that the travel time impacts are localized and asymmetric, particularly along high flow motorway segment. So the main message from us is that the criticality should not be assessed from topology alone. The most relevant elements are not only central in the graph, they are also central in the use network. These are some of the main references which we use in this work. Thank you for your attention. Now, if you have any question, any acknowledgement, the floor is yours.
Thank you, Tahseen. I have a couple questions, but let's see if the audience has any first.
Okay.
Okay, I will go then. Your results, you seem to only measure like localized, well, not only localized impact, but you kind of, as I understood it, reduced the capacity of a particular link and then looked downstream, looked farther downstream, looked upstream, and looked at
And
ramps.
on the ramps. Yep.
Yeah, exactly. But I think you had said earlier that you're going to look at total system travel time as your performance metric. So do you have a sense of how removing or reducing the capacity of one of these nodes impacted the entire network?
Yeah, this is the total performance, system performance of the network. This is not just a specific link, but like we reduce the capacity of the specific links based on the between centralities.
Yeah.
And then we recompute the assignment model in the software, and
Yeah.
it computes the whole system travel time, not just the specific one.
Yeah, but do you have that measure, like what the value is?
Yeah, I have that value,
Okay.
but here in this case is this in the percentage, and when I reduce these specific nodes like 37900 and 37894, so the whole system travel time is reduced by 6.88%.
Got it. So this is the whole system
This
travel
is the
time.
whole system travel time.
Very nice. And then my I guess maybe suggestion for your future work then is like
Yeah.
you've identified for your case study area that it is really corridor specific where the centrality is. It'd be interesting to see like if you start to remove more and more and more links along that corridor,
Yes.
where is the tipping point where the network performance really does start to degrade?
Okay, it's a very good question at the moment. And for me, like, if I understand correctly what you are saying, so I'm now trying like the behavior which we got from the analysis is the corridor level based. So each node and link lie on the same motorway.
Right.
So in my mind, like I have to aggregate all these nodes and all these links to make an aggregation of the same links which is situated on the same motorway, and then we'll see that if I reduce the capacity of that aggregated links, like it will be like maybe it will be in 100, maybe it will be in numbers like 50 or something like that. So it will increase the whole travel time in like I would imagine in drastic way.
Yeah. Okay, very good. I don't
Thank
see
you
any
so
other
much.
questions, but this is really interesting research, and I totally agree with your premise that we need to look at what's going on the links in terms of flows, not just the network structure itself.
Of course, of course.
Okay, let's move to our next speaker then. We have JohnPaul from FAMU-FSU College of Engineering to talk about airport level aircraft turnaround time performance. You can introduce yourself, JohnPaul. Actually, are you here? Ooh. Yes, you are. We can see your screen, the results section.
Hi, everyone.
Hello, we can hear you. And yeah, it looks like you're going to go into presenter mode now.
Okay. Can you see my screen?
Yes, you're in good shape. Take the
Okay.
floor.
Hi, everyone. My name is JohnPaul Adimonyemma. I'm currently a PhD candidate at Industrial and Manufacturing Engineering here at FAMU-FSU in Florida. So I'll be talking about airport level aircraft turnaround time performance analysis and the contributing factor identification for a major US airline. So today I'm going to give a general overview, the motivation about this study, and our findings in the current state of the literature, and then present the methodology, and then data and feature engineering, and then present the case study and also conclusion. So to better understand this very well, we know that for aircraft turnaround process, it begins when an aircraft arrives at a designated parking spot, of which we can call a gate or a remote stand. And it also ends when it departs from a parking location for its next flight. So this process is very important because it connects both an inbound arrival to its next outbound departure, right? So when an aircraft lands at its parking spot or the gate, several activities are being carried simultaneously. Some can be sequential, some can be done in parallel, right? For example, passenger boarding, baggage handling, referring, and the rest of them. But this shows us that the turnaround time process is also very, very important because if not optimized very well, it can result to departure delays. Now, improving turnaround execution is very important for airline reliability and also cost. So, like I said earlier, several activities in this turnaround process can be done sequentially, for example, cleaning and boarding, and some can also be done in parallel, for example, offloading and refueling. And here we show a simple event process, for a turnaround activity. Now, in the literature, this process can be stochastic, and a delay in one activity can block others, ultimately causing a chain of delay reactions. Now, evaluating the performance of this turnaround turnaround time process at network of airport level is very, very important. Not just looking at an individual flight airport. So in the literature that I conducted, I discovered that prior studies mainly focus on prediction and optimization of all these several activities that occur during the turnaround time. And also, most of those studies also focused mainly on individual airports without having an overview of the network of several airports. And also, present studies focus on predictions, that is using machine learning, and we know that and they lack interpretable frameworks. So having an interpretable framework to better understand how several factors affect poor performance of turnaround time is very key for a major airline here in the US. So our research contribution, first of all, we developed to better understand how different factors affect the turnaround performance. We developed what we call an airport aircraft turnaround performance metric. So that actually captures the actual versus the scheduled turnaround time. And then in order to compare that at different airports, we average that across all turnaround flights for each airport day. Now, given the development of that particular turnaround performance metrics, we now engineered operational features that characterize turnaround performance. Now, these features are based on the real world activities that really happened using a major airline data set as a case study. And then having developed these performance metrics and also engineered operational features, we now use interpretable models to explain what factors affect the performance of this turnaround time and process. So to give an overview of the analysis that has been done in this work, first of all, we did a thorough data cleaning, of which I'm going to explain later. And also, I'm going to also present the performance matrix that was designed to understand how the turnaround performance differ at different airports, and also the feature engineering, and also the modeling. So a basic setup to understand the turnaround process. For example, assuming this is a single flight, now the aircraft needs to arrive at the gate. So this is what we call, this is the scheduled arrival, gate arrival. Now, so this aircraft is scheduled to arrive at this particular time. Now, and then, however, the actual arrival starts from when the aircraft actually arrives and taxis towards the gate. So this is when the turnaround time starts. Now, between this particular point, several activities are also conducted. For example, baggage offloading, baggage unloading, passenger boarding, pilot arrival, flight attendant arrival. However, some of these activities can be done in parallel, while some of them are also can be done sequentially. So after all these activities have been done, now the turnaround time ends when the aircraft departs from the gate to the next destination. So just to show a snippet of what happens in a real world case study, for example, so I'm going to consider a single flight, and for this particular flight, we could see the time at which the aircraft arrived to the gate, the actual time, and we could see that it arrived before the scheduled gate arrival, right? And also, it also departed before the scheduled gate departure. So for this particular flight, this aircraft is the turnaround time is assumed to be on time. So how do we quantify the performance, the turnaround time performance at different airports? So we designed a metric for that. Now, the metric is given as this. So basically, is the ratio of actual gate arrival is the ratio of the departure and arrival. And we could see that this is averaged over all the aircraft and over all the airport, and also in each day. Now, to better interpret this, right? So when this ratio, when this ratio is less than 1, what does that imply? So it implies that the turnaround is completed on time or ahead of schedule, as we saw in the previous slide. Otherwise, if this ratio is greater than 1, that means the turnaround efficiency is rated low. So this means that operational improvement or adjustment is also needed. So the reason why we have to average this all over the airports and in each day is to provide a comparable analysis between major airports and of what I would call the top airport and the low airports, right? Such that major airports with high volume of flights are not penalized. So the data set that were used, I'm not going to provide detailed explanation about that because of it's high classified. So the data set that was used in this analysis contained over 1.2 million flight records. So each row represents a flight record. And that covers over 237 airports. Basically, it contains both US airport and non-US airport, but we focus our analysis on US airports. And just to give a general overview, 40% of flights were actually delayed based on the data sets over approximately, and that could range from 5 minutes to 3 hours. So now, given the nature of the data sets that we obtained, we conducted a thorough data cleaning process, of which I'm going to explain later. Now, but just to give some basic overview, high-level overview, so we have aircraft-related features, for example, the fleet, the seats, how many seats, how many passengers, minimum operational ground time, that is the time required to complete a particular turnaround, and several other features. Now, turnaround time events are being can be caused by several delays, and here I show several delays and primary delay reason of which a delay can happen, right? So we could say that most of them are as a result of late arrival of equipment, and also we have let's say flight attendant late arrival, delay in loading and offloading, and other type of delay reasons. So to better assess this data set very well, so we performed a cleaning process. So the first thing we did was conduct a quality check. So whenever the gate arrival is greater than a departure time, so we kind of verify the legitimacy of gate arrival and departure time. So if the departure was not later than the arrival time, we kind of drop those rows or those flight records. And also missing data we are also obtained. We also present in the data set. Now we have the 85% of the pilot and flight attendants data missing. Also, we also look at the time window. So any events that are beyond the arrival and departure was also removed. Then to standardize the analysis, we consider turnaround events that happened during the day, basically. So we exclude overnight turnaround by removing rows where it occurred between 8 p.m. and 5 a.m. And the actual turnaround time exceeds also 260 minutes. So at the end of the day, out of over 1.2 million data sets that were present, carrying out this detailed and this meticulous data cleaning process, we're able to result to 957,664 data records. So, having understood the data itself, now we need to design features that will help us explain the performance of this turnaround time at different airports in each day. Now, the main motive behind this feature engineering is that, first of all, we want to ensure that every feature represents how turnaround were actually executed. So there are some features that occur after the turnaround time window. We don't include that. Now, some features also have redundancy effect on other features selected. So we try to eliminate those features. Now, at the end of the day, these several features were selected, and we categorize them into activities during the turnaround time, which also includes deviation in passenger boarding, deviation in baggage loading, deviation in baggage offloading. And like I said earlier, some of these events also can occur in parallel. So we also kind of capture that. We also capture features related to aircraft and passenger, and we also capture features related to airport traffic characteristics. So now, based on the results, first of all, we present the distribution of this turnaround of this metric, YIT here. Now, when we look at this particular graph, we could see that this ranges from 0.01 to up to 7 now, and we could see a far right tail here that implying that at this particular point, the delays are very high. Now, only few, based on the data set that we obtained, only few were able to achieve the turnaround time process on time. Now, in general, 48% of the airport days data considered completed on and were completed on time, while 52% exceed their planned turnaround duration. And when we look at which of these airports that have high impact, on poor turnaround performance, so we could see different based on the top 10 airports. We could see at Dallas ranking first, and then some of these airports in Miami, in Chicago, and the rest of them. Now, the median performance is close to 1 at all the major airports. So, recall that we are trying to analyze both the system, how this turnaround time performance occur at the system level, whether the delay is systematic or whether it is just at the airport level. Now, at a high level, these are the factors that are affecting this poor performance, right? Now, considering the underlinear analysis, we discovered that the deviation in passenger boarding causes much more delay in turnaround performance based on our analysis. And when we also look at the nonlinear comparison of that, we could see that passenger delay, the passenger delay deviation also causes poor turnaround time performance. However, even though some of these features were not statistically significant, we could also see that they exhibit some nonlinear effect, and that was also captured by the SG boost analysis. For example, the deviation in baggage offloading was captured as not having great impact here. But when we look at the nonlinearity effect here, we could see that it also has some much more impact on the performance of the turnaround time event. So we explored several how they disperse, right, in terms of feature contribution. So the most important feature here that contributes to this poor turnaround time delay is the delay in passenger boarding, right? And then across all the airports, for each of these airports, so we further explore whether these factors affect delays at each of these airports, for example, the top 10 airports. And we could see how these factors contribute to poor performance of turnaround time at at each of these airports. And in terms of the feature contribution, only one particular feature can contribute up to 30 to 40%. Top 2 features can also contribute to 50 to 65%. And also top 3 to 4 features can also contribute approximately 80% based on this plot here. So in conclusion, one thing this study has tried to answer is that, first of all, turnaround performance is shaped by a number of operational features whose effects can be nonlinear, can be heterogeneous, and also airport dependent. So in general, the delay affecting, let's say, Tallahassee Airport might be different with that affecting that of Dallas Airport. Now, given the features that we are able to derive from this, the deviations in passenger boarding, completion, and also baggage loading consistently emerged as the most influential operational factors affecting turnaround delay. Now, these features remain influential everywhere, but their impact differs across different airports. And in conclusion, most of these factors also remain consistent with what has been discovered in earlier studies. Thank you. And with that, I'm going to end my presentation. I look forward to your questions and further discussions.
Thank you very much. Sorry if I missed it, but where did you get the data for this analysis?
Okay, so this data is in partnership with a major US airline. Yeah.
Okay. Yeah.
Yeah.
Got it. Very good. And then so you're going to make conclusions around the boarding time being a significant factor. Does that include people getting off the plane, deboarding, and people getting on the plane, or is it just people getting on the plane?
Okay, so basically here we just capturing passenger boarding.
Okay.
Yeah.
Okay. Very nice. Yeah, I mean, great job getting the data and great job doing this analysis. It's very interesting.
Thank you.
Okay. Others have questions, please put them in the chat, or you can raise your hand now. I'm gonna move to our last speaker, who is Buddhi Wirasiha, the PhD candidate at Erasmus University Rotterdam in the Netherlands. His research focuses on floating ports and governance, examining floating terminals as strategies for port expansion and offshore logistics. His work centers on the Port of Rotterdam's energy transition and the development of an offshore multi-purpose hub in the North Sea. I did do one study on this one time, so I'm looking forward to seeing what a researcher who actually focuses on this topic can produce compared to myself. So, Buddhi, go ahead.
Yeah, thank you, Professor. And am I audible enough?
Say it again.
Am I audible enough? Can you hear me?
Can hear you quite well, yeah. No slides yet, though.
Okay. Can you see my slides?
We can see them in the presenter slides. So you got to probably swap it.
Can you see them now?
Yes, good.
Okay, great. Okay, so good afternoon, everyone. I'm Buddhi Wirasiha from Erasmus University Rotterdam, and today I will talk about floating offshore terminals for the energy transition, and I will mainly focus on how these systems have evolved and what opportunities they may create for future green hydrogen and ammonia supply chains. And first, I would like to briefly explain where I'm coming from. And my PhD is part of a floating future research project. Within this project, I mainly work on the economic value and governance side of floating infrastructure. But floating future is much broader than transport or ports. And the overall project basically, it looks at how floating infrastructure could be developed for future. And one important reason is space scarcity. And many industries are facing increasing pressure on land and available space, for example. So the broader question is whether we can move some infrastructure onto water. And my research looks at this question mainly from port and logistics perspective, and especially focusing on governance angle. So with that background, let me first introduce the world of floating ports and terminals. And I'm starting from the middle of this figure with cargo. In shipping, we know that we have different vessels for different cargo types, as same as in road transportation. And a container ship looks different from an oil tanker, and a bulk carrier has another design. So same idea applies to floating terminals. And from the outside, many of these systems may look like vessels, but their design and functions depend on the cargo they handle. So we can have floating systems for containers, dry bulk, break bulk, and ro-ro, and even for liquid bulk specifically. But for this study, we are focusing on liquid bulk, and even within that, we are focusing on energy, because this is because floating energy systems are much more mature. And for the other side of the story, which that cargo group shown on the left, and there are still relatively few real applications. When we started looking at this mature energy area, we found an interesting problem, and there is already a large amount of research, but the knowledge is separated. That means the oil research mainly talks about FPSO and offshore production separately, and LNG research talks about FLNG, FSRU, and LNG carriers, and other studies focusing only on storage or transfer or another single function. And now we see that hydrogen, ammonia, and other new energy carriers are entering the discussion. So we have a lot of knowledge, but the problem is it sits in different research silos. So the missing part is understanding how these pieces connect as one logistic system. So based on that gap, this systematic review has two main objectives. First, we map how energy commodities, logistic functions, and floating system types are connected in the literature. And then using that understanding, we look forward and we explore how floating offshore terminals could support future green hydrogen and ammonia supply chains. So the study first understands the past and present, and then uses that knowledge to explore the future. To do that, we first had to map the existing floating terminal landscape. For the review, we followed the PRISMA framework as suggested in the literature. In simple terms, PRISMA helped us structure the identification, screening, selection, and synthesis of literature. So we searched Scopus and Web of Sciences. At the beginning, we identified 637 records. After removing duplicates, we had 496 unique studies, and we then screened these studies based on their relevance to floating infrastructure, maritime logistics, and energy supply chains simultaneously. And finally, 279 studies were selected for the main analysis. And after that, we coded these studies using 3 dimensions, and we then used FOSS-Weaver, a tool to map how those dimensions are connected using clustering mechanism. And finally, because hydrogen and ammonia systems are still emerging, so we complemented the review with 12 expert interviews. And so the study combines systematic review, coding, network analysis, and expert knowledge together. And this slide simply shows how we captured literature. One group of keywords focuses on floating systems, such as floating production, storage, terminals, and etc. The other group captures maritime logistics and different energy commodities, and we combine them to reach literature from several research areas rather than searching on only for one technology, and so on. Once we selected 279 studies, we asked 3 simple questions for each and every paper. First, we ask which energy commodity is this study describing. Second, we asked which function is being discussed in each and every paper. For example, whether it's production, storage, or transfer, and what is this exact function. And finally, we asked which floating system is being discussed. For example, is there any specific floating system such as FPSO, that means floating production, storage, on offload, and such as maybe FLNG or something like that. So simply, from this point onwards, every study is represented through these 3 coding dimensions: energy, function, and system type. A single paper can have several codes, and this allows us to see connections between topics that are normally studied separately. Before moving to the connections, we try to map their timeline separately. First, we looked at how energy commodities change over time. And the early literature is mainly about crude oil, then natural gas, and especially LNG become much more visible. And the longest, and also we see the strongest growth appears from around 2010 onwards. And more recently, we also start seeing hydrogen, ammonia, carbon dioxide means demand for carbon capture, and also other transition-related energy carriers. So the energy landscape becomes much more diverse over time. And we see a similar change in their functions. At the beginning, floating systems mainly provided storage and transfer. later we see production, liquefaction, regasification, and logistics support becoming more important. And recently also we see some kind of new functions such as floating bunkering also appear. So floating systems move from a few basic functions toward more complex and multifunctional logistic roles. And the same development appears in the floating system types. FPSOs dominate the earlier period, then FLNG, FSRUs, and LNG carriers grow strongly with the development of LNG. And this is also where floating infrastructure becomes very useful, and it can also provide flexible capacity when demand changes or when permanent infrastructure is not yet available. And today, we are beginning to see new concepts, including hydrogen or ammonia-oriented floating systems. And here's the most important part. Then we brought all three dimensions together, and from that network, we identified three main clusters. The first cluster is mainly the traditional hydrocarbon world, and FPSOs, crude oil production, storage, transfer, and shuttle tankers are strongly connected in this cluster. And also the second cluster is mainly the LNG world, and here FLNG, FSRU, LNG carriers, liquefaction and regasification from a much more connected supply chain. And third cluster is emerging energy transition area. Here we start seeing hydrogen, ammonia, carbon dioxide, synthetic methane, bunkering, and different conversion functions. And so the network moves from traditional hydrocarbon system through LNG and low carbon systems towards much more diverse green energy space. So, and on the next slide, I will show that these three clusters also have a very clear timeline. So rather than only calling them three clusters, here I would also describe them as three phases of floating energy systems. The phase one is oil-centered period, and floating systems mainly support offshore production, storage, and export. And FPSOs become integrated production and logistic hubs here. And in phase two is the formation of LNG chain. And now we have specialized floating assets for different parts of supply chain. And FLNG supports liquefaction, and LNG carriers provide transport, and FSRUs provide storage and regasification. At the receiving side, we can see that. And also, then we reach phase three, and here the system starts becoming more diverse, and hydrogen, ammonia, carbon capture, bunkering, and different conversion functions enter the network. And so the important finding is that floating energy infrastructure has continuously changed according to the needs of the energy system. And that brings us to the main future question: what comes after phase three? So to explore that future or the question, we focus mainly on green hydrogen and ammonia here. Before identifying floating opportunities, we first need to understand these two supply chains. Let me start with hydrogen first. Hydrogen can be produced in several ways. The green route uses renewable electricity, such as wind or solar, together with electrolyzers. The blue route normally uses natural gas, but captures the carbon dioxide. The gray route also uses natural gas, but without carbon capture. So, and we also have routes linked to nuclear power and high emission fuels, which is brown. Once hydrogen is produced, it can be transported as gas through pipelines or as liquid hydrogen, but liquid hydrogen requires around minus 253 degrees of Celsius. That creates major challenge and transport challenges. Now ammonia is strongly connected to the supply chain. As you can see, to produce ammonia, we need hydrogen and nitrogen. So hydrogen is an input for ammonia production. But the relationship also works in the other direction. Ammonia can be transported and later cracked back into hydrogen. So ammonia can act as a hydrogen carrier here. So this is important because ammonia is much easier to store and transport than liquid hydrogen. So it is normally transported at around minus 33 degrees of Celsius, and the maritime industry already had decades of ammonia shipping experiences. So this creates a strong connection between two supply chains. We also see demand for this connection at port level, especially when we are discussing with experts in Port of Rotterdam. For example, future import infrastructure may need to receive ammonia, store it, and potentially use it as a source of hydrogen. So rather than linking these only within the supply chain, that means rather than thinking about hydrogen and ammonia as two completely separate systems, it becomes useful to think about them together. So based on literature review and 12 expert interviews that we ask questions from experts that we then ask, where could floating terminals actually fit within these supply chains? So we identified opportunities across upstream, midstream, and downstream supply chains. So upstream, we could have a green hydrogen FPSO and located near offshore wind and producing hydrogen directly at sea. And another option is green ammonia FPSO. Even some of the companies now started developing this, and where hydrogen is converted into ammonia for easier storage and maritime transport. In the midstream, one opportunity is floating hydrogen liquefaction, although this is technically challenging. A more near-term option could be floating ammonia storage and ship-to-ship transfer, especially where ports face land and storage constraints, because ammonia is toxic. So some of the people, they don't like to have ammonia storage nearby their houses. So then downstream, we see opportunities for floating bunkering and import terminals, and ammonia appears closer to practical application, while hydrogen may require some time. The FSRU provides an important reference for how floating import terminals could develop. And so these are not just predictions, and there can be possible future configurations based on existing technologies, literature, and also expert insights. And of course, there are limitations here. Within the study that we have conducted, the review only covers peer-reviewed journal papers and from Scopus and Web of Science, and coding is based mainly on titles, abstract, and keywords due to the time constraints. And also our 12 experts were selected for their expertise rather than geographical representation. And there are also several important future research directions that we can notify. We need to understand the real opportunities for hydrogen ammonia and also their operability in terms of operating in offshore systems. And we need more research on modular platforms and multi-commodity hubs in the difficult conditions such as in North Sea. So then we need to test them and understand whether is it operable. And also we also need to understand governance, classification, investment, and conditions between floating terminals and the shore. And those are the potential future research directions that we can notify. And also, I will finish with 4 main messages. The first, floating energy systems have evolved from hydrocarbons to LNG and now towards multi-energy systems. And second, these spaces are connected through shared logistic functions such as storage, transfer, liquefaction, regasification, and bunkering. Third, the ammonia currently appears to be the nearer term floating opportunity, mainly because its maritime logistics are already more mature. And finally, technology alone is not enough, and future development also it depends on regulation, demand, investment, and coordination between different actors. So floating terminals could become an important part of the future green energy supply chains. And once again, this research is part of the Floating Future Research Project. So I would like to acknowledge the project consortium and the Dutch Research Council for their support. And I also thank my co-authors and everyone who contributed to this study. And thank you very much for your attention. And please feel free to contact me if you have any further questions. And for now, I am happy to open the floor for questions and discussions. And thank you so much for listening.
Thanks very much, Buddhi. As usual, if the audience has questions, please chime in. Unfortunately, your last slide kind of took my question from me already, which was what is the kind of near-term use case? And you mentioned ammonium kind of leading the way because of the existing technologies.
Yeah. And also, companies are really trying to invest on ammonia import terminals, but the problem is the special issue in the port areas.
Okay. I mean, obviously, why you do research is because you're intellectually interested in it, but I'm wondering if there was any other impetus for this. I know you had the sponsors, but were there particular use cases they're looking into, or they just wanted to have a general sense of what the state of the academic literature is and such?
And actually, in the consortium, we are working with 2 case studies with the actual partners. And for example, companies such as Wopak, the energy companies that are trying to invest in future green energy supply chains, such as ammonia. So they are really looking at on floating, whether is it a potential option for them. And also in North Sea, it's a real case that we are working on this offshore multipurpose hub to understand what kind of functions that we can replace in these offshore systems other than investing in port systems.
Yeah. And one of your co-authors put a question to the rest of the audience about if other countries are looking into floating concepts. I honestly don't know. The study I referenced earlier was actually not in regards to energy, but rather containers at LA Long Beach, basically differentiating between like medium time sensitive and medium value goods that maybe don't make sense to fly across the Pacific, but also are really harmed by the delays at the port. If you could somehow prioritize those, put them on top of the container, get them to a offshore port, and then air flight them to inland ports was kind of the general idea. But that was just a academic idea, nothing that's anywhere near implementation. And as far as energy goes, I'm not the right person to ask.
Yeah, thank you for that answer.
Okay, before we go, I want to thank Baldev Giri, who was the one behind the scenes, making sure everyone could present and could speak when you wanted to. So thanks to Baldev. And I think this concludes BTR, although you maybe can catch the end of another session in the last 20-minute here. But thanks to all the speakers, thanks to the audience, and hopefully see you in person sometime in the future or BTR next year.